How the fraction of rebreathing defines machine CO2 absorbent and agent use efficiency during the maintenance phase of anesthesia. I would like to thank Rick, Sophie, and Francis, and many others here to help collect the data here that I'm about to present. What is the fraction of rebreathing? How do different anesthesia machines differ? How does a fraction of rebreathing look like in vitro? What can it tell us about anesthetic agent use? And how does fraction of rebreathing, fresh gas flows, relate to CO2 absorbent usage and agent usage? What is the fraction of rebreathing? It's a fraction of the exhaled gas that's being re-inhaled. It's the fraction of the tidal volume made up of rebreathed gas. And intuitively, we know that if we lower our fresh gas flows, we'll be rebreathing more. If we increase ventilation, we will be mixing more. And, oh no, it's the other way around. So if the fresh gas flow decreases, we will be rebreathing more. Likewise, if the ventilation increases, we will be mixing more, and there will be more rebreathing as well. I'm going to give you an example in which we are using 100% of oxygen, and I'm ignoring many complexities. This is our anesthesia machine here with our fresh gas flow, our inspiratory limb, the lungs, expiratory limb, and the ventilator. And let's say I'm ventilating with 5 liters per minute, for example, 10 times 500 milliliters. And let's say my fresh gas flow here is 5 liters per minute. Under these conditions, there will be no rebreathing. So the fraction of rebreathing will be 0. The entire tidal volume here, sitting ready to be delivered during the next inspiration, consists of fresh gas only. If I lower my fresh gas flow to 4 liters per minute, the rebreathing fraction will be approximately 0.2. That is, the next tidal volume contains about 20% of rebreathed gas. If we lower it to 0.5, it's going to be 50%. So the next tidal volume contains about 50% of the rebreathed gas. If you go down to 1 liter, it's going to be 0.8 or 80% of rebreathed gas. And actually, if I'm going down to 0.18, it's going to be 1. Why 0.18? Because I have to give a very small amount, of course, to provide for the oxygen uptake by the patient. So there's going to be full rebreathing. The CO2 is going to be removed. Everything else will be re-inhaled. But I have to provide about 18 milliliters per tidal volume if my respiratory rate would be 10 to provide for the oxygen taken up by the patient. And again, I'm assuming I'm just using oxygen. So if I plot this relationship, it looks as follows. On the x-axis, you have the fresh gas flow, and on the y-axis, you have the fraction of rebreathing. Obviously, if the fresh gas flow is higher than minute ventilation, you have no rebreathing. And you can see that as you lower the fresh gas flow, you get a linear relationship here with the fraction of rebreathing. And actually, it stops here right at where your oxygen consumption is. When the fresh gas flow has been lowered to what your oxygen consumption is, you're working closed, and the fraction of rebreathing is 1. And actually, the flow height displays the rebreathing fraction here. You can see at the bottom here, the rebreathing fraction is 50%, and you now know what that means. Why is the fraction of rebreathing important? Because it affects the vaporized dial setting required to maintain a constant and expired concentration with different fresh gas flows. And basically, most of my ideas come out of the book of Low and Ernst, who described this 30 years ago. So basically, for 30 years, I've been experimenting clinically with what these authors wrote. So what did Low and Ernst do? This is a circle breathing system here with the vaporizer and the fresh gas flow, and they looked at how much anesthetic agent was contained in each part of the circle breathing system. In other words, they did mass balances, and they looked at how much agent was going in, how much was present in the inspiratory limb. They took into account oxygen uptake, nitrous oxide uptake, anesthetic uptake, CO2 production. They looked at how much agent was being exhaled, And here you can see the fraction of rebreathing, and 1 minus the fraction of rebreathing, and the fraction of rebreathing denotes the fraction that's being re-inhaled, and 1 minus FR denotes the fraction what James was talking about a minute ago. And they put it all together in a formula, and it's called the general anesthetic equation. And what this equation says is that if you are ventilating a patient with a certain ventilation, certain alveolar ventilation, a certain dead space, and you want to maintain a certain constant and expired concentration of an agent of which you know the uptake pattern, then it becomes possible to predict the vaporizer dial setting over time to do this with different phase gas flows. And this is how we did that clinically. This is the general anesthetic equation using empirical patient data. And you can see here the time axis. This is the fresh gas flow on a logarithmic scale. And this is the vaporizer dial setting of sevoflurane. And these are all combinations to maintain the same end expired 1.8% sevoflurane concentration. With a high fresh gas flow, you can see that with each of these fresh gas flows, high and low, there is a progressive decrease in vaporizer dial setting over time, which is a reflection of the fact that uptake decreases. But there's something else here, and that's the fraction of rebreathing. If you look, for example, at 60 minutes, and you're working with a fresh gas flow of 8 liters per minute, all the way right here, and you then lower your fresh gas flow, you will have to increase the vaporizer dial setting because of rebreathing. Now we know that different anesthesia machines have different rebreathing characteristics. Why is this? Why may this be? Well, let's have a look at how the components of the circular breathing system are organized. This is the lung here. This is the fresh gas flow. For example, in the ACES, the fresh gas flow inlet is proximal of the inspiratory limb. In the ADU, it's distal from the inspiratory limb. The Zeus anesthesia machine is working differently altogether. It's the gas in the circle system is continuously being mixed, and the injector adds the vapor and the carrier gases. And of course, the flow eye is an entirely different concept as well. And we know from Eager from many years ago that the manner in which these components are organized do have important effects on anesthetic agent. This is Michael Laster. It's veterinary doc for his animals. And this in the back here is a discussion we were having on the second gas effect as proposed by Phil Payton. So, coming back to the importance of the fraction of rebreathing and different anesthesia machines. Do different anesthesia machines have different fraction of rebreathings? Since the manner in which the components are organized differ, then wouldn't it make sense to think that that's our hypothesis? We hypothesized, well, maybe then the fraction of rebreathing differs. And Francis Rijkaard, one of our residents, did a great job trying to address this in vitro. And what we did was the following. We have an anesthesia machine, a ventilator, and we have an empty canister here, no canister. And this is a flow meter, and it is feeding about 80 milliliters, 80 milliliters into the tip of this balloon. And we are then ventilating this balloon with 5 liters per minute. And we are progressively decreasing the fresh gas flow from 7 to 0.3 liters per minute. And we did this for 5 different anesthesia machines, 3 different times. And the idea was, of course, since there's no absorbent present, we know that as our fresh gas flow is lowered, there will be more and more rebreathing. So the FiCO2, the CO2 concentration in the inspiratory limb will rise. The lower the fresh gas flow, the higher the FiCO2 if you have no absorber in the system. And we thought, well, because different anesthesia machines have different rebreathing characteristics, this relationship might differ. And the idea was, if we have 3 different anesthesia machines, if the fresh gas flow is 5 liters per minute, and we're ventilating with 5 liters per minute, there will be no difference between the machines. because there is no rebreathing. Once the fresh gas flow is higher than minute ventilation. And at the other end of the spectrum here, if it's closed, it's closed. There shouldn't be a difference either. Then maybe, maybe there's a difference here somewhere. Maybe machine A here is reusing more of the exhaled gas, and you get a higher FiCO2, and with another machine, it's different. And actually, they're all the same. Regardless of whether you're using an ADU, an ACES, a Flow-I, or a Zeus, the FiCO2 is exactly the same. And actually, if I plot instead of FGF here, instead of and you can see that the relationship looks like this. And I'm now going to plot the fresh gas flow as 1 over the fresh gas flow, and then you get a straight line. You can actually do a linear fit to it. You can see that the parameters of these fits here are very, very similar. Excellent fit here, and these lines do not seem to differ a lot. At least we were not able to extract huge differences. Interesting though, at the other side here, at the high fresh gas flow side, where we did not expect any differences, we did find differences. And I'm zooming in here on the high fresh gas flows. And you can see that if you use an ACES anesthesia machine, once the fresh gas flow goes above 5 liters per minute, there is indeed no rebreathing. But there is rebreathing with the other anesthesia machines. Now, the clinical implication for me is if you're using a TIVA technique and a circle breathing system, don't put in a CO2 absorber because it will be used, ultimately it will be used up. Use high fresh gas flows and place an HME filter. Okay, now, the hypothesis was we have different anesthesia machines, probably different rebreathing characteristics, but we see that the fraction of rebreathing, as we define and measure it, doesn't differ. What are the implications then for us clinically? Since the fraction of rebreathing doesn't differ, well, then maybe the vaporizer dial settings with the different fresh gas flows for the different anesthesia machines during the maintenance phase of anesthesia are the same. In other words, could this general anesthetic equation be general? Well, we examined this clinically. We examined what the vaporizer dial settings were over time to maintain an end-expired concentration of 1.8% over a wide range of fresh gas flows with an ADU, older data, and a Flow-I. And on the left here, then Sophie collected all these data. On the left, you can see the vaporizer dial settings with the ADU over time with the different fresh gas flows, the dark blue surface, and here with the Flow-I. So I'm now going to superimpose them on top of one another. And you see the surface on the left, they match pretty well. And if I actually express those ratios as a percentage, they're 100%. I mean, if I take the average of all these values, it's 99.9. You see some fluctuation, but I think that has to do with differences in patient uptake in certain fresh gas flow groups. We also said, well, why don't we go ahead and compare the ADU with the Zeus also? So we previously did studies in which we looked at what kind of fresh gas flow and vaporizer dial settings we needed with the ADU to maintain a certain end-tidal concentration. We now applied those to the Zeus. This is something that Sophie presented at the ESA this year. And guess what? So we applied a certain fresh gas flow vaporizer dial setting sequence with 3 different fresh gas flows, 4, 2.75, and I think about 8 or 12 patients in each group. And the important number is this here, 5. So a prediction error of only 5%, which means that if you expect 2%, you get 1.9 or 2.1. I'd say that's pretty good. So again, I think this suggests that they're pretty similar. How now are fresh gas flows and the other parameters, and the other factors here that interest us, that is canister agent usage and canister usage, CO2 absorbent canister usage, and ACES usage interrelated. I'm going to start off again on the left upper part here. This is how I started off at the beginning of the lecture. the fraction of rebreathing decreases linearly as fresh gas flow is lowered. The vaporizer dial setting has to be increased inversely proportional with the fresh gas flow. If I plot the surface on a 3D plot where I have 1 over FGF, this becomes a straight line. And actually, if you look at agent consumption with the ADU, the ACEs, and the flow I with different fresh gas flows, with the Vivo fluid expressed as milliliters per minute, as milliliters liquid, for an Untitled of 1.8, and again, I'm only talking about the maintenance phase, there we find little difference. Okay, what about CO2 absorbent usage? Well, again, this is how I started off. This is the fraction of rebreathing. And we notice that as we lower our fresh gas flows, the FiCO2 increases. And if I plot this on 1 over FGF, I get a straight line. I'm now going to go to the second lecture about CO2 absorbers. So if we actually, there is a way to plot canister life as FCU, and we also see that, that the fraction of the canister that you use per hour increases as linearly as the fresh gas flow is decreased. And if I can predict this, then I can predict this, then I can come up with a cost model. The only thing that I was missing was how well do these data match in Vivo data, because these are all empirical data, patient data. These were in vitro studies. And I'm going to go to the next. I'm going to try to go to the next lecture, and I'm going to take a very short. Here, this is a picture of our family vacation at the beginning of July. And we were cycling past Faxe in Denmark. And actually, it's a large, and we were driving past this plant. And some of the leaves were starting to turn white. And this is actually a limestone, an open mine, where they get mines. So it's a lot of fun with the kids because they can go fossil hunting, and so can the adults. And we learned, for example, that the limestone is actually burned, and the calcium oxide is then rehydrated. You get calcium hydroxide. It's mortar or cement. So this is what's in most of our many of our CO2 absorbents, but it's used for a variety of purposes. Also in cement, for example, if you build a house, you put cement on the bricks, it will get rid of the CO2, it will attract CO2 out of the environment and get rid of the water. And there's your wall, there's your brick wall. Okay, so this is the second part here, in vivo canister life. What we learned during the last 2 NAVAt sessions was that we need CO2 absorbers. Why? Because we can re-inhale everything but not the CO2, because too much CO2 is toxic. How high does the CO2 go if we do not have a CO2 absorber in our circle breathing system? This is an in vitro test with the ACEs, and I was feeding I think 180 milliliters or 160 milliliters into the tip of the balloon of the 2-liter bag we were ventilating, and you can see that as we lower our fresh gas flow, the FiCO2 goes up to very high percentages. Actually, if your fresh gas flow is 320 and your CO2 inflow is 160, 1/3 of it is CO2, so you get 33% of CO2, which is more than 200 millimeters of mercury. 2% you get a headache and dyspnea after a while. 4% dyspnea in minutes. 6% you get hearing and visual changes in a few minutes. And note that if we would not be using a CO2 absorber in a circular breathing system, this is what we would be getting with a 1 liter per minute fresh gas flow. And 9% is the lowest published lethal concentration. We need CO2 absorbents. But what about the lower end of the spectrum here? 0.5% inspired CO2, is that acceptable? 1%? Well, let's ask Captain Kirk here. These are the spacecraft maximum allowable concentrations, the SMACs for CO2. And you can see that in space travel, 0.5% is deemed acceptable for 1,000 days. 0.7% a week to half a year, and even 1%, 1.3% up to a day. So this seems to be well tolerated. The question then is, what's the effect of the inspired CO2 on the entitled CO2? Well, the effect is simply additive. Let's look at our cadnogram here. If my FiCO2 rises by 0.5%, which is about 4 millimeters of mercury, then the entitled CO2 will rise by the same percentage. And this is what matters for a patient, because that's what reflecting the arterial PCO2. So in most of our patients, a 0.5% or 4 millimeter rise is perfectly acceptable. But so what? What does 0.5% FiCO2 gains? Well, up to 100% of canister life with some absorbance. And occasionally you see early breakthrough with some canisters. I mean, I've seen it like 1 out of maybe 50 canisters I tested, and the FiCO2 goes immediately to 0.1 or 0.2, and often you can just leave it be, and they last for as long as the other ones. But that's just anecdotal. So, for the remainder of this lecture, I'm going to assume that the FiCO2 replacement threshold is 0.5. We tested the in vitro canister life of several canisters that fit onto the ACES, which we published online a few months ago. And I'm going to go over the products again: mSorb Plus, low flow sorb, Medisorb, EF, Medisorb, Spherosorb, Little Lamp Spiralit. First thing to note is that these are all calcium hydroxide based absorbents, except for this one here, the Spiralit, that uses lithium hydroxide. Within the calcium hydroxide group, you have those with sodium hydroxide as a catalyst. The importance of this is that these may degrade inhaled anesthetics, but even so, the clinical significance of this is questionable. The Little Lamp contains a different catalyst, lithium chloride. It's also important to note that these canisters differ with regard to the weight, the contents that they contain. And here are the results of our tests, and what's on this graph here is, so what we did was we ventilated the balloon, and we were feeding CO2 into the tip of the balloon, 160 milliliters of CO2 per minute. We were ventilating it with an ACES anesthesia machine, 10 times 500 milliliters, and then we tested each of the canisters, some with 4 liters, some with 3. So we tested the canister life with each of the different products over a wide range of fresh gas flows, and this is actually how long they lasted with each of the fresh gas flows. So the higher up on the figure, the longer they last. So let's have a look at what happens here with a 350 milliliters fresh gas flow. And this is a new plot. I actually plotted this myself only a week and a half ago. Here you can see the weight, the actual weight of product in each of these containers. The color refers to the product. And this again is the hours until the FiCO2 becomes 0.5. So the higher up here, the more efficient they are for us clinically. This is the mSorb Plus, and this is the low flow sorb. They do not contain any catalyst. This is the Medisorb EF. It contains a little bit of catalyst. These are the products that contain lithium chloride as a catalyst or sodium hydroxide. And if I then plot them together and do a linear fit, I end up with a line here that says that 100 grams of product gives about 1.5 hours of lasts about 1.5 hours. Again, this is Spiralit. This is an entirely different product. If these are oranges, this is an apple, because it's lithium hydroxide based. This is all calcium hydroxide based. And then it's up to you to decide how clinically important that is, but it's clear that catalysts here seem to add canister life. They're higher up, but they also happen to be those that are most filled. Okay, now the question is, are these results valid in vivo? Because in vivo the situation is different than in vitro. In vitro we have a continuous CO2 flow. In vivo you have different fresh gas flows, you have periods of non-use, overnight, over a weekend, etc. They may lead to different temperature gradients, and this may all have an effect on canister life. So we tested 5 canisters, the Amsorb Plus, the low flow sorb, the Medisorb, and those two, somewhat arbitrarily, but I did happen to get 4 calcium hydroxide based canisters with different catalysts and the spirolet. And what we did was I asked the anesthesiologist, this is actually a study done by Karen de Jong, use the same anesthesia machine as in vitro. We're going to use the same anesthesia machine as we used during when we were testing our in vitro, testing the machine in vitro with the different canisters, and we left all aspects of care to the anesthesiologist. But except for the fresh gas flow, we told them you're going to use either 0.5 liters per minute or 6 liters per minute. So either there's going to be the same degree of rebreathing, 0.5 liters per minute, or no rebreathing, a high fresh gas flow. And then we told them you're going to use this canister until the FiCO2 is 4 millimeters of mercury. To make sure that we took into account other confounding variables, we made sure that the duration of CO2 pneumoperitoneum was the same, because more CO2 pneumoperitoneum is more CO2 load. That the minute ventilation and the expired CO2 was the same, and that the weight of the patient was the same, because obviously larger patients would may produce more CO2. So I'm going to present the results of 4 canisters each, except for the little arm. I just happen to have a 5th one. Age, height, and weight of the patients in the 5 groups did not differ. Duration of CO2 pneumoperitoneum, minute ventilation, and then the expired CO2 did not differ. And here I'm going to plot results in a similar fashion as before with the in vitro results. And this again is the content, the initial weight of the products sitting in the plastic container. And here again on the y-axis is the time until the FiCO2 reached 0.5%. Spirolet, Amsorb Plus, Medisorb, low flow sorb, and little lime. You can see there's a large variability here within each group, obviously because CO2 loads differ. And I'm going to add the in vitro results here, because remember the question I had was, my in vitro data, can I use them to do some modeling? Do they really present what's happening in vivo? And what we found was that basically these in vitro results seem to represent reasonably well what's happening in real life. Okay, this was the last part I needed to solve the agent consumption and CO2 absorbent puzzle. But in order to do so, I need to do one more thing. I need to convert these data into something that allows me to calculate the cost of the canisters. So again, here are the different products. The lower the fresh gas flow, the shorter they last, of course. But I can't use these data to calculate costs. So I'm going to present them in a slightly different manner. I'm going to go back here. This canister, for example, lasts 50 hours. And that means that 2% of that canister is used per hour. Another canister may last 20 hours, for example here. That means 5% of the canister is used per hour, and if it lasts 12.5 hours, it's going to be 8%. So that's the percentage of the canister that we use per hour under these conditions. And if I then plot the results, I get this. Again, it's just a linear relationship. As the fresh gas flow is lowered, canister usage increases linearly as fresh gas flows are lowered. Okay, now how are we going to calculate costs then? Well, it's a simple high school math. This is the equation of a straight line, the different products with the slopes and the y-intercepts, which you can find on this graph. If this is the FCU, this is fresh gas flow, this is the slope of the line, this is the intercept, and we published all these intercepts for different products, for different inspired CO2s, so you can calculate this yourself. If I know the fraction of the canister I use and I multiply it by cost, I get the euro per hour. So one quick example, 0.7 liters per minute fresh gas flow. I'm going to use little lime, so the slope for little lime is here, the y-intercept for little lime is there, that's the fresh gas flow, 0.7. That's the percentage per hour. I'm converting it into a fraction per hour. Then I look up the cost of one canister, and I multiply this with this, and I get the cost of a canister per hour. Yesterday in the workshop, I provided a huge Excel file that allows you to calculate the costs of the different canisters with whatever settings you like. Now, and this is, I'm going to a conclusion here. If I lower the fish gas flows, I'm going to use less agents, but more CO2 absorbers. What happens to the costs if you combine them? This is the cost here. Oh, sorry, this is fish gas flow. This is milliliters of liquid sevoflurane used to maintain anesthesia for 55 minutes with 3 different anesthesia machines. So there's an almost linear decrease up until here if the fish gas flow is lowered. And there's a linear increase in canister usage. So this really makes it easy for me to calculate the costs for whatever scenario you like. And the question is there a magic optimal flow at which the combined cost of agent and absorbent is minimal? Well, so far all the cost calculations I did indicate that there is no minimum. This is an example. ACES, little lime, 18 euros, 160 milliliters CO2, 1.5% Vivo, 0.39 euros per liter. And you can see that as the fish gas flow is lowered, the cost of the Vivo decreases, but not to the extent that the two cross. And again, notice that there's a little bubble here. That's just because these are empirical data. So this really wraps it up. I think we have now all the data to allow you to do your own agent usage and CO2 absorbent usage comparisons for whatever Untitled you'd like to use, for whatever canister you'd like to use, for whatever FiCO2 threshold. So if you're interested in that, come and see me. Thank you.